Right, if you look on the board up here, you've got a way of imagining what's going on in electricity. As we've seen, electricity is really mysterious, it's a really difficult idea to understand, and the reason for that, I think, certainly, is two things. In an electric circuit, there is charge going round. There's little negative electrons are going round and round and round, and at the same time, energy is being delivered. Okay? Energy is going out of the battery and being delivered to the bulb. Okay? This is why electricity is a difficult idea, is because you've got two things happening at the same time. Charge is circulating round, and energy is being delivered. Okay? But as I said, if you think about the postman coming to your house, delivering some parcels, and then getting in his or her van and driving back to the sorting office, it isn't that hard to understand, really. Okay? The key thing, I emphasised this last time, is the way that you picture electricity in your mind. The way not to picture electricity in your mind is like flowing water. Although there are lots of words and lots of things that use that idea, it's a very bad idea. Charge, circulating is the easier of the two to understand. That's okay if you think of water going round. But voltage, which is linked to the energy being delivered, that becomes pretty much impossible. And that's the difficult one that we need to sort out. Okay? The charge going round, we measure that using electric current in amps, and the energy being delivered, we measure that using voltage in volts. That's why there are two things to measure about electric circuits, because there are two things happening. If you can move over to this diagram then, this is a picture then, a mental picture, a thought picture if you like, of what's going on inside an electric circuit. Okay? In reality, electrons are doing all kind of mad things. That's very hard to picture. If you think of electricity like a system of like little railway tracks, okay? Think of the little railway trucks leaving the battery. They come down here along the track to the bulb, they go through the bulb and back to the battery. Just like a post van coming from the sorting office, round to your house and then back again, all right? So on this picture, what's circulating is to think of little railway trucks circulating, okay? That might seem a bit mad, but really all we're doing is saying each little truck is like a little bundle of electrons, okay? Picturing electrons going around is quite difficult, but if you think of each little bundle of electrons like a little truck, little railway truck, then you'll be able to get the right answers, okay? So this is our picture. I hope you've got it in your books now if you didn't have it before. Trucks going around like this. Now, the trucks leave the battery, and as we said last time, the way that we understand this is what's happening in a battery is energy is being put in. So if you can add to your battery, energy is being put into each truck, okay? That's why it makes no sense to talk about a battery going flat and needing recharging, okay? The charge is the trucks or the electrons going round, they don't vary at all. What's happening is the battery is using the chemical energy stored inside it and it's putting it into the trucks, and when the battery has run out of energy and can't do that anymore, it's gone flat. What we mean by that is it's run out of energy, okay? So if we draw the trucks here, they're all going to be loaded up with some lumps of energy, okay? The trucks coming out of the battery will be loaded up with energy, okay? The wires behave like little railway tracks, they just don't really do anything. So particularly in exam questions where all wires are perfect, the trucks go along the wire and they come down here to the bulb. And I hope you can see, of course they'll still be full of energy. Assuming the wires are perfect, they're just like railway tracks, number of people who get on at one station, hopefully are the same number that arrive at the next station. So the amount of energy in each truck is going to be the same, okay? Now, if the bulb is beaming away happily, I'll just point out to you that means it's giving out light energy and it's giving out some heat energy, all forms of energy. Can we picture then, can somebody remind us what we're picturing is going on inside the light bulb? On the truck picture, basically the bulb is taking energy out the trucks, and that's what I want you to draw here, is a truck and it's having its energy taken out, okay? Very, very important. The bulb is using up the energy delivered by the electricity. It is not using up the electricity. It's not using up the charge, the electrons, the trucks. They go sailing through. And again, if this sounds a bit tricky, again, think of a postal service. They come to your house with their van, they deliver the parcels, and then the person gets in the van and they drive off. It's the energy that's being delivered, not the postal vans that are being used up. Unless your dad's a postman, obviously. Okay? Now, one rule that works on this system, with one rule about the truck picture, is the trucks have to come back to the battery empty. Okay? We'll talk about why that is a bit later, but the trucks have to go back to the battery empty. Okay? So, when they come out of here, obviously, they're going to be empty because obviously there's nowhere else to lose energy as they go back to the battery. So trucks are loaded up by the battery. They arrive at the bulb takes the energy out and uses it and turns it into light and heat, and off it goes into the universe, and then the trucks go back empty to the battery. Okay? You might think, what have we achieved? Not very much. We've got a silly way of thinking about electricity. But actually, we can use this to sort out the mystery of voltage and current. All right? And this is something that's going to be quite useful to you. If you can look at circuits and work out voltages and currents, then you're going to be well up. Okay? Now, what do we mean? Let's take the easy one. Let's do current first. Current, as you know, is measured with ammeters. So just pop a couple of ammeters in there. All right? You should know already, ammeters measure electric current. And we need to be able to imagine what an ammeter is actually doing. And a really good way of thinking about it, I think, is to imagine it's a bit like a turnstile. If you've been to a football ground or a big stadium or something, you go through the turnstile, which is basically counting as you go through, or up on the underground or on the train or something. One of those barriers that just counts the number of people that have gone through. Okay, that's a bit like what the ammeter does. Okay, it sits in the flow of the electricity and it simply counts trucks. Okay, the ammeter basically tells you. Let's take an example. Let's suppose the ammeter read 3 amps. So we put our ammeter in here, it read 3 amps, okay? What does that mean? It means that 3 trucks are going past every second. So next time you set up a circuit and it says 3 amps or something like that, hopefully now you've got a picture in your head of what's going on, okay? And for the level of physics you guys are moving into, that's important. You've got to work stuff out to think about what's going on. And this will allow you to do that, all right? So an ammeter reading 3 amps means 3 trucks going past every second, okay? What's this ammeter going to read? Yep, that's a good way of explaining it. This ammeter here, if you think about it, is going to also read, sorry, they're going uphill now, which looks a bit bizarre, but you get the idea. There's still going to be 3 trucks per second, and it's still going to read 3 amps. Many people get a bit confused by this, and they think, well, some of the electricity's been used up, so it should be less here. You're absolutely right, but there's one word in that sentence that's wrong. If I looked at this and I said, oh, I don't quite get that, some of the electricity's been used up, the bulb's using up electricity, so there should be less electricity here. That sentence is perfect, apart from one word. What's being used up here is energy, not electricity, not the trucks aren't being used up. And the very important thing to understand about an ammeter is it's only interested in the number of trucks. If you want your diagram to be super accurate, these trucks here were fully loaded with energy. These trucks here are empty. If you'd spotted that, you're absolutely correct. What effect does that have on the reading of an ammeter? Nothing. Because an ammeter simply counts the number of trucks. It doesn't look inside to see how much energy there is. It simply counts the number of trucks. So this ammeter will read 3 full trucks per second, and this one will read 3 empty trucks per second. But ammeters only tell you the number of trucks, and that's why they'll both be the same. Where could I put the ammeter in the circuit so it didn't read 3? Whereabouts could I put it in the circuit so it gave me a reading that wasn't 3 amps in this circuit? Yeah, exactly. Nowhere. Wherever you put in this circuit, can you see? If 3 trucks per second leave the battery, how many arrive here? How many of you ever got the train maybe? If it's just a straight line, 3 trains per second go there. Well, next station it would have to be the same, wouldn't it? Unless it was some kind of horror version of Thomas the Tank Engine. Thomas, Percy and Gordon set off into the tunnel. But only Thomas and Gordon came back and Percy was never seen again. I'll cut that bit out, it's a bit silly, isn't it? Can you imagine that as a film? You'd go and watch it, wouldn't you? Anyway, do you get the idea? As the gentleman said, it's not the trucks that are being used up. The trucks are not being used up, okay? So ammeter will be the same all the way around. So, is everybody happy then what we're measuring with current? Current is measured by ammeters in amps, and what it's measuring is the number of trucks going around per second. Okay? Now, let's move on to voltage, which is the more difficult one. This is the one people get bothered by because it isn't just like a sort of stream of stuff going around. Okay? Let's put a voltmeter across the bulb. Okay? Let's see how a voltmeter works. And you can do this on your diagram, connect a voltmeter across your bulb. Okay? Now, voltmeters basically work in a slightly different way. First of all, they're not connected in the flow. When we do some circuit work and you actually connect stuff up, it's really important you put your ammeter in series. Think of the turnstile. It's no good building a turnstile at your new football ground and putting it in the middle of the car park when everyone's going into the door over there. You're not going to get any kind of reading. It's got to go in the flow. It's got to go in series in the circuit. Voltmeters sit at the side, either side of things, which we call in parallel. Okay? Before we look at the voltmeter, let's just have a look at what the battery's doing. Okay? To understand how voltage works, we need to sort out what the voltages are in this circuit. And you'll notice I've chosen a 12-volt battery. Okay? Would anyone like to guess what happens differently in a 12-volt battery compared to a 6-volt battery? You know what a battery does, and you'll have noticed if you ever bought a battery, the important thing to get right is the voltage. There's 1.5 volts, 6 volts, 9 volts, 12 volts. What's the 12, do you think? Bit of imagination, bit of guesswork here. What do you think the 12 actually means? If you could see this loading up of the trucks going on, what do you think the 12 actually represents? Any ideas? Basically, in a 12-volt battery, how much energy is put into each truck? The answer is 12 joules. That pen's not very good. Into each truck, gentlemen, goes energy. That's true in any battery, but in a 12-volt battery, you put 12 joules of energy. All right? So you can go back and improve this label. Sorry, my pen's a bit wonky. In a 12-volt battery, if you can imagine like a little production line, it puts 12 joules of energy into each truck. Moves the truck on, 12 more, 12 more, 12 more. Each battery, a 12-volt battery, beg your pardon, puts 12 joules of energy into each truck. Okay? So the trucks here don't just have energy, they have 12 joules of energy in each one. Now, let's go back to our voltmeter. Trucks coming along here, well, they're still going to have 12 joules of energy because they come along a perfect piece of wire. The ammeter doesn't affect anything, just counts them, so it doesn't affect the engine at all. Trucks coming out of here are going to have 0. Now, it's very important to understand how a voltmeter works. It takes a truck with each arm, it looks at the amount of energy per truck, and it takes them away from each other. It works out the difference. If you've done any reading on electricity, what's the other way we sometimes talk about voltage? It's sometimes called, you sometimes hear voltage referred to as potential difference. You may have seen that. And you might just think, oh, it's an old-fashioned word for it. It's a much better word for it. The amount of energy in each truck is called potential. You could make a potentiometer where you just go, you stick it in the circuit, it says 12. We'll see in a moment why that's not very useful. A voltmeter doesn't quite do that. Hence, if you think of voltage, think of potential difference. It measures the potential here. Potential sounds very grand. It's simply the amount of energy in each truck. Potential here 12, potential here 0. Potential, maybe put PD there or something. Potential difference is 12 volts. Okay, so voltage is the difference, potential difference between the amount of energy in the trucks in the two sides where you connect it. Okay, so this voltmeter, gentlemen, will read 12, but you need to be clear why. We're going to see later on trucks with more than one bulb in, circuits with more than one bulb in. It's reading 12 because it's the difference. It's not reading 12 because that's got 12. It's reading 12 because that's got 12 and that's got 0. Okay, it might seem a small point, but it's important. All right. Now, what would happen then, let's say you've understood it, what would happen then if I put a voltmeter there? You never see this in exam papers or in textbooks, but it's a really good question. Think what would happen. This arm, if you were thinking 12, you're on the right track, that would read 12. And that one would read 12 as well. And the sum 12 minus 12 is 0. So it's going to read 0. The difference between 12, which I remember potential difference. It doesn't read potential. It doesn't read 12, it doesn't read 12, it reads the difference between 12, which is 0. And you might think that's a bit strange, because if I got connected to that electricity with that energy, that's quite dangerous. What does it mean? 0? What's 0 about the train? They're all loaded up with 12. What exactly is a voltmeter telling us? What does this 12 mean for the light bulb? Maybe think about what the voltage would read if you put it across the battery. Think what that would read. 0, 12, it would obviously read 12 volts. What does the 0 mean about this bit of the circuit? Let's make the question a bit clearer. What's 0 about that bit of the circuit? Because the trucks are all fueled up. How much energy is leaving the circuit here? How much energy is being put into the circuit here? How much energy is leaving or entering the circuit here? You see? Nothing. You might want to put this in your margin. Voltage is to do with how much energy is entering or leaving the circuit. Energy coming into the circuit, e.g. battery. Energy going out of the circuit, e.g. light bulb. That's what voltage is about. It's how much energy is going into or out of the circuit. I'll say that again. It's to do with the amount of energy going into or out of the circuit per truck. How much are trucks gaining in the battery? 12. You could call it plus 12. How much energy is being taken out in the bulb? 12. You could call it minus 12. But how much energy is leaving or entering the circuit between here and here? Nothing. It doesn't mean they've got no energy. It means they're not gaining energy and they're not losing energy, just rolling down the track. Okay? Voltage is the tricky one, but I'm hoping you can now start to picture in your mind what voltage means. Okay?